It's my pleasure to present our work on universal few-shot instance perception using point representations called UniFS. This paper focuses on unifying four fundamental subtasks in a few-shot learning context: object detection, instance segmentation, pose estimation, and object counting. The first challenge lies in unifying task representation. Instance perception tasks differ in data, features, and outputs. For example, object detection involves scenes with multiple objects, while pose estimation focuses on single objects. These differences make it hard to create a unified multitask few-shot learning approach. To address this challenge, we reformulate instance perception tasks into a unified point representation learning approach. By using user-defined point annotations, the model learns task-specific points for each query image. For example, in object detection, points are placed along bounding box edges, and in instance segmentation, they are distributed along the mask contour. Another challenge is constructing a unified model architecture that can effectively learn to solve multiple tasks. The architecture must be flexible enough to adapt to each. Current approaches often rely on task-specific formulations, incorporating separate learnable components and training objectives for each task. The most common method is to add a dedicated task head for each individual task. However, such designs tend to become increasingly complex and less scalable as the number of tasks grows. Our UniFS model has a unified architecture with three key parts: the feature extractor, the point decoder, and the point head, which together handle various instance perception tasks. The feature extractor, based on a pre-trained RESNET101, extracts features from both support and query images. For support images, point features are extracted using ground truth points, while for query images, an RPN generates regions of interest, and ROI-align pools these regions into query object features. The point decoder, using self-attention and cross-attention, captures relationships between support and query points. Self-attention refines query point features, while cross-attention aligns support points with query image features to reduce representation gaps. Finally, the point head processes refined point embeddings through an MLP to predict offsets from RPN anchors, generating final point coordinates. This unified design efficiently addresses multiple tasks with a streamlined structure. The last challenge we face is establishing a unified learning paradigm. Traditional L1 and L2 losses focus on individual point errors and ignore relationships between points, leading to ambiguities. For example, as shown in Figure A, L1 and L2 losses can be identical for points on different shapes, missing overall structure. To improve this, we propose structure-aware point learning, which considers point relationships by supervising angles between a point and its neighbors, like theta 1 and theta 2, shown in Figure B. This approach reduces errors from noisy annotations and enhances robustness. Additionally, SAPL incorporates a sign function into the loss to better capture details at sharp angles and improve shape accuracy. This method uses angles from one-hop to n-hop points for more effective, structure-aware learning. We visually demonstrate UniFS's effectiveness and generalization to novel categories. The model adapts to various tasks by following instructions and using different point annotations, showing its flexibility and ability to handle diverse instance perception tasks. We visualize the impact of structure-aware point learning in UniFS. With SAPL, the model learns object structures better, producing accurate contours. In contrast, the L1-only model fails to capture point relationships, leading to uneven boundaries and incorrect boxes. We tested our method against task-specific and multitask few-shot models on the COCO UniFS dataset. It performs competitively, especially in one-shot scenarios, making it well-suited for few-shot tasks. It also excels in few-shot object counting, outperforming models trained specifically for that task. On the Pascal 5i benchmark for few-shot object detection, our method exceeds state-of-the-art models, demonstrating its effectiveness in few-shot detection tasks. We conducted ablation studies to evaluate the impact of several key components: multitask learning, structure-aware point learning, the number of points used, and the number of transformer blocks. These studies confirmed the effectiveness of our network. Thank you for listening.